Hello everyone, this is Professor Keene. We've been talking about Chapter 4 of A Student's Guide Through the Great Physics texts. In this chapter, we're looking at the relationship between falling objects, their speed, and pendular motion. The puzzle we discussed in the last lecture was why it is that two objects that are made of the same material, limestone for example, will fall with different speeds in the same medium if they have drastically different sizes. So for example, if you drop a rock underwater, it will fall to the bottom of the pond rather quickly. And if you drop a piece of silt underwater that's made of the same material as the rock, it will fall very slowly. Why is this? Well, buoyancy cannot account for this effect, but what Salviati argues is that the drag affects them differently. In particular, since the drag depends on the surface area, drag becomes relatively more important for small objects, and that is why they fall more slowly. That's a topic we discussed in my last lecture. Before this chapter ends, there are a few more questions that Simplicio and Sagredo bring up to Salviati to discuss, so I'd like to just kind of run through those last few questions before we move on to the next chapter. So, final questions. Let me use my thing here. So, final questions for chapter 3. For chapter 4. Okay, so we've been talking about how drag is able to slow down objects falling through a medium, right? It has a more pronounced effect for small objects, but it has a less pronounced effect for very heavy objects. But this raises the question, I'll call this question 1. So can the resistance or the drag of the medium, the resistance or drag exerted by a medium such as air or water or whatever, by a medium, check the acceleration or reduce the acceleration to 0, check the acceleration of even the heaviest bodies, so of any and all bodies falling, given enough time. So if you have some very heavy body, like a cannonball, falling through the air, we've just argued that the drag has not a very big effect on it compared to a small grain of silt. But still, is that drag enough to eventually make the acceleration of this large cannonball go to 0? So in other words, will the acceleration eventually approach 0, and so it will reach terminal velocity, you might say. So this is on page 52. This is one of the questions that arises. Okay, let me just run through the second question first before we answer this one. So question 2, this has to do with pendula specifically. So if the period of a pendulum, does not depend on the weight of the bob or the angle through which you pull it, and release it, pull it back. Remember, these 2 points were things that Galileo is arguing for, right? It does not depend on 1, the weight of the object, or 2, the angle through which you pull it back. Then is there anything that it depends on? Is there anything at all that the period depends on? Can you change the period of a pendulum? And the answer is yes, the length. Okay, so for example, the length, and he's going to say yes, it does depend on the length of the string that you use to suspend it. So that's question 2. Okay, so let's go back to question 1 and answer this. How does Salviati answer this question on page 52? He says that we know that the air will slow down a cannonball. It will check the acceleration. So even air, which is very thin medium, air slows a cannonball. How do we know this? How did Galileo know this? What arguments did he provide for how he knows that air does in fact slow down a cannonball? Well, he thinks of an experiment that you can do, and I'm not sure if he himself actually carried this experiment out. But imagine you were to take a cannon and you were to aim it. So here's kind of a rudimentary cannon, and you kind of rig this thing up so that it aims straight down at the ground. Okay, so it's going to shoot your cannonball straight down at the ground. Okay, so it's kind of like a pivot or something. And maybe here's the ground, and it's got like some region like this, and you fire the cannonball straight at the ground, and it makes a hole in the ground at the bottom when you fire it. And you look at how big the hole is. So the cannonball makes a large hole when shot straight down, when aimed straight down, kind of at point blank range when you shoot it. Okay, but what if you were to take the same cannon and instead of aiming it straight down at the ground, you were to put it on a cliff and aim it straight down from up on the cliff? Okay, so here's your cannon. You shoot the cannonball down from the cliff, and you look at the size of the hole it makes when it hits the ground here. So in this case, the cannonball, Galileo argues, makes a comparatively smaller hole when fired from a cliff, fired downward. What does this tell us? What is the implication of this data? Well, presumably the size of the hole that it makes is related to the speed that the cannonball is going. It's also going to depend on the size of the cannonball too, but if you use the same size cannonball in both cases, and it makes a bigger hole when you shoot it straight down here and a smaller hole there, then it must be going at a higher speed right when it leaves the cannon than when it falls for a significant distance. What does this mean? This implies that the air does in fact slow down the cannonball. So it's going to have some extremely high velocity, a high muzzle velocity coming out of the cannon, and it's going to have a lower velocity after traveling through the air for some time. So the air does exert a drag on the cannonball, and if you were to fire this from very, very high speed, from very, very high heights, eventually the cannonball would stop accelerating as it falls. It would reduce to terminal velocity, and it would go at a constant speed the rest of the way down. So the resistance or drag exerted by the medium, even a thin medium like air, is enough to check the acceleration of falling bodies. This is the argument that Galileo gives. Okay, let's move on to the next question. Answer 2. Is there anything that the period of a pendulum does depend on? And the answer is, like I said, yes. It depends on the length of the string. Here, there's an interesting digression here that Salviati goes on to. Let me read a short section of the text. This is on page 53. He says, we can do these experiments with different pendula and look at the time it takes for them to swing back and forth. So here's one pendulum. Here's another one with a different length. This one's length 1, this one's length 2, and measure how much time now it takes to swing back and forth, how much time it takes this one to swing back and forth, and you'll find that the times are different. This might take time t1, this one might take time t2, and we're going to find that t1 is going to be less than t2. This one's going to swing back and forth rapidly. This one's going to take a while to swing back and forth. Okay, and here's where, I'll say more about this in a moment, but here's where Salviati mentions that we come now, this is the bottom of page 53, we come now to the other question relating to pendulums, a subject which may appear to many exceedingly arid, dry, or boring, especially to those philosophers who are continually occupied with the more profound questions of nature. Nevertheless, the problem is one which I do not scorn. I am encouraged And here's where Galileo compliments Aristotle. He says, I am encouraged by the example of Aristotle, whom I admire, especially because he did not fail to discuss every subject which he thought in any degree worthy of consideration. And then Salviati goes on to say, impelled by your queries, I may give you some of my ideas concerning certain problems in music, a splendid subject upon which so many eminent men have written. Among these is Aristotle himself, who has discussed numerous interesting acoustical questions. Accordingly, if on the basis of some easy and tangible experiments, I shall explain some striking phenomena in the domain of sound, I trust that my explanations will meet your approval. And then Segredo replies, he says, I shall receive them not only gratefully but eagerly, for although I take pleasure in every kind of musical instrument and have paid considerable attention to harmony, I have never been able to fully understand why some combinations of tones are more pleasing than others, or why certain combinations not only fail to please, but are even highly offensive. So there's going to be an interesting digression that we will go into in the next chapter that is going to be related to pendulum motion, and this has to do with why it is that certain musical notes, when struck together, sound pleasing and others sound discordant or not harmonious. And Galileo is going to employ the kind of discussion he's going to have here on the swinging of pendulums to understanding why notes, certain ones sound good together and other ones do not. Okay, so we'll get into that more in the next chapter, but I just wanted to bring that to your attention here because it's something, there's some foreshadowing in the text. Okay, so let's talk for another moment about the length of a pendulum and how it affects the period of oscillation. Galileo provides some examples of experiments of different lengths of pendula and the periods that they take to swing back and forth. And you'll see by amassing the data that he provides, you will find that the period of a pendulum is proportional to the square root of the length of the string. Okay. What does this mean? It means that if you have a pendulum of a particular length and it has some period, if you quadruple the length, the period would be doubled. So if the length is quadrupled, then the period is doubled. Right? It's not enough to simply double the length to double the period. If you double the length, the period would go up by a factor of the square root of 2. You need to quadruple the length in order to double the period. So if, for example, L2 is 4 times L1, then T2 is going to be equal to 2 times T1 in this example we gave above. I'll ask you this question, see if you can figure it out. What would it take to triple the period? So if you wanted this one to have 3 times the period of this one, what would you have to do to the length? So if we want T2 to be equal to 3 times T1, then L2 would be equal to what? Okay, so I'll let you think about that. Okay, let me say one other thing here before we move on, and that Galileo doesn't always talk about the period. He sometimes talks about the frequency of oscillation. That is, not the time it takes to swing back and forth, but how many swings it makes per second, let's say. And so we just need to keep in mind that the frequency is the inverse of the period. The frequency is defined as 1 over the period. So for example, if something has a period of 10 seconds, then the frequency would be 1/10 of a hertz, or 1/10 of a cycle per second. This is nowadays measured in hertz. That's not the units, of course, that Galileo used. Heinrich Hertz isn't until late 1800s, early 1900s. Anyhow, it's sometimes reported that the frequencies of pendula depend on their lengths, and so you'd see right away here that the frequency of a pendulum is proportional to 1 over the square root of its length. Okay, and I guess let me say one other thing before we move on. Let me drag these over to here. I've been just talking about this in terms of proportionality, but there is actually an equation that relates these. This is not something Galileo talks about, but this is going to come in handy later on, and I'm not going to derive this. I'm just going to tell you what it is right now. that if you want to know the period of a pendulum, it's going to be equal to 2 pi times the square root of the length over the gravitational acceleration in its vicinity. So this you can see, this by the way works to, this is an approximate formula, but it works quite well for low amplitude swings, small angle swings. Notice here that the period is proportional to the square root of length, like I mentioned here, but it also is proportional to the inverse of g. So for example, if you were to swing a pendulum instead of on Earth, where g is 9.8 meters per second squared, you were to swing it on Mercury or Venus, where g is different, it would have the same pendulum with the same length, would have a different period. Okay, I'll stop there, and we will move on to chapter 4 next time.